The requirement for an #8 equipment grounding conductor or EGC pool lighting, specifically in wet niche luminaires, as outlined in National Electrical Code Section 680.23b2, addresses a critical safety concern related to fault current pathways. The code mandates that where non-metallic conduit is used for the pool light circuit, an #8 American wire gauge copper EGC must be installed within that conduit, unless a listed low-voltage lighting system is in place. This EGC needs to be terminated in the forming shell junction box or transformer enclosure. The underlying reason for this requirement centers around ensuring a robust and reliable path for fault current in the event of an electrical fault within the pool lighting system. While it's true that a #12 American wire gauge EGC might be sufficient as the minimum size for a 120-volt circuit EGC according to Table 250.122, the #8 American wire gauge EGC serves as a redundant and more substantial grounding conductor. Its primary purpose is to provide an alternative path for fault current should the smaller #12 American wire gauge EGC become compromised or fail. There are several scenarios in which the #12 American wire gauge EGC could potentially fail, including physical damage during installation, corrosion over time despite the materials used being relatively corrosion resistant, or a break in the conductor due to mechanical stress. In such cases, the #8 American wire gauge EGC acts as a backup, ensuring that a low impedance path to ground remains available. This is crucial for the proper operation of overcurrent protection devices, such as circuit breakers or fuses, which need a sufficiently high fault current to trip and energize the circuit in a timely manner. If the fault current path is too weak or non-existent, the overcurrent protection device might not trip, leading to a prolonged fault condition that could pose a significant safety hazard. The larger #8 American wire gauge EGC offers a lower impedance path compared to the #12 American wire gauge EGC. Lower impedance means that for a given voltage, a higher current will flow. This higher fault current is more likely to trigger the overcurrent protection device quickly, minimizing the duration of the fault and reducing the risk of electric shock or other hazards. The concern about corrosion, while valid in electrical installations, is not the primary driver behind the #8 American wire gauge EGC requirement in this specific scenario. The wet niche luminaire is designed to be submerged in water, and the materials used, including the copper EGC, are selected for their resistance to corrosion. However, even with corrosion-resistant materials, the possibility of corrosion cannot be entirely eliminated, especially over extended periods of time. The #8 American wire gauge EGC provides an additional layer of protection against the potential effects of corrosion by offering a more robust conductor that is less likely to be completely compromised by corrosion. It's important to understand that the National Electrical Code prioritizes safety, particularly in potentially hazardous environments such as swimming pools. The requirements outlined in the code are designed to minimize the risk of electrical shock and other hazards, even in the event of unforeseen circumstances or equipment failures. The #8 American wire gauge EGC requirement for wet niche luminaires is a specific example of this principle, providing a redundant and reliable grounding path to ensure the safety of individuals using the pool. The code focuses on preventing situations where a single point of failure could lead to a dangerous condition. By requiring the larger EGC, the code addresses the potential for the smaller EGC to fail, ensuring that a fault current path remains available. It's essential to adhere to all applicable codes and standards when installing and maintaining electrical systems, especially in environments where water is present. Proper grounding is a critical aspect of electrical safety, and the #8 American wire gauge EGC requirement for pool lighting is a specific example of how the code addresses this issue. When dealing with electrical installations near water, it is always recommended to consult with a qualified electrician to ensure that the work is performed safely and in accordance with all applicable codes and regulations. Firstly, understand the code requirements. The National Electrical Code, specifically Section 680.23b2, dictates that when a metallic conduit is used for wet niche pool luminaires, an #8 American wire gauge copper EGC must be installed within the conduit. Secondly, consider the purpose of the EGC. The primary role of the EGC is to provide a low-impedance path for fault current back to the source, enabling overcurrent protection devices to quickly trip and energize the circuit in the event of a fault. Thirdly, address potential failure points. While the #12 American wire gauge EGC might be adequate under normal conditions, the #8 American wire gauge EGC serves as a redundant path in case the #12 American wire gauge EGC fails due to damage, corrosion, or other factors. Fourthly, recognize the importance of low impedance. The larger #8 American wire gauge EGC offers lower impedance than a #12 American wire gauge EGC, facilitating a higher fault current and faster tripping of overcurrent protection devices. Fifthly, remember that corrosion is a factor. Although the materials are designed to resist corrosion, the #8 American wire gauge EGC provides an extra margin of safety against the potential effects of corrosion over time. Sixthly, acknowledge safety prioritization. The National Electrical Code prioritizes safety in potentially hazardous environments like swimming pools, and the #8 American wire gauge EGC requirement is a specific measure to minimize electrical shock risks. Seventhly, realize the code addresses single points of failure. By requiring a larger EGC, the code mitigates the risk of a smaller EGC failing and leaving the pool area without a proper fault current path. Eighthly, always consult a qualified electrician. When working with electrical installations near water, it is crucial to seek guidance from a qualified electrician to ensure compliance with codes and safe practices. Ninthly, prioritize proper grounding. Proper grounding is essential for electrical safety, and the #8 American wire gauge EGC requirement is a specific example of how to achieve it in pool lighting. Tenthly, adhere to all applicable codes and standards. Compliance with all relevant codes and standards is non-negotiable when installing and maintaining electrical systems, especially in environments where water is present. Imagine a scenario where the #12 American wire gauge EGC, which is part of the 120-volt supply circuit to the pool light, suffers a break due to mechanical stress or corrosion within the junction box or conduit run. Without the #8 American wire gauge EGC, a ground fault within the pool light could result in the metal parts of the light fixture becoming energized. This could create a dangerous situation for anyone in the pool, as they could come into contact with the energized metal and experience an electric shock. However, with the #8 American wire gauge EGC in place, the fault current would have a low impedance path back to the source, causing the circuit breaker to trip quickly and to energize the circuit, preventing the electric shock hazard. The #8 American wire gauge EGC provides a level of redundancy and safety that the smaller #12 American wire gauge EGC alone cannot provide, especially in the harsh environment of a swimming pool where exposure to water and chemicals can accelerate corrosion and degradation of electrical components. Let's examine the differences between copper and aluminum conductors. Though the #8 American wire gauge EGC is required to be copper, it is helpful to understand the characteristics of aluminum too. Firstly, conductivity. Copper has a higher electrical conductivity than aluminum, meaning it can carry more current for a given size. Secondly, corrosion resistance. Copper generally has better corrosion resistance than aluminum, especially in wet or harsh environments. Thirdly, tensile strength. Copper has higher tensile strength than aluminum, making it less susceptible to breaking or stretching under mechanical stress. Fourthly, weight. Aluminum is significantly lighter than copper, which can be an advantage in some applications. Fifthly, cost. Aluminum is typically less expensive than copper, making it an attractive alternative in cost-sensitive applications. Sixthly, code restrictions. The National Electrical Code has specific requirements for the use of aluminum conductors, including restrictions on direct burial and the use of aluminum conductors in certain wet or corrosive environments. Seventhly, termination methods. Aluminum conductors require special termination methods to prevent corrosion and ensure a reliable connection. Eighthly, thermal expansion. Aluminum has a higher coefficient of thermal expansion than copper, which can lead to loose connections if not properly installed. Ninthly, ampacity. Aluminum conductors have a lower ampacity than copper conductors of the same size, meaning they can carry less current. Tenthly, applications. Copper is generally preferred for high current applications and in harsh environments, while aluminum is often used in overhead power lines and other applications where weight is a major concern. In the context of pool lighting, the choice of copper for the #8 American wire gauge EGC is driven by its superior conductivity, corrosion resistance, and tensile strength, ensuring a reliable and safe grounding path in this demanding environment. The National Electrical Code (NEC) provides specific tables for determining the minimum size of equipment grounding conductors based on the size of the overcurrent protection device protecting the circuits. These tables, such as Table 250.122, specify the minimum size of the EGC based on the ampere rating of the circuit breaker or fuse. However, the NEC also allows for the use of larger EGC than those specified in the tables, and in some cases, such as pool lighting, it mandates the use of a larger EGC, such as the #8 American wire gauge EGC, to provide additional safety and redundancy. The decision to require a larger EGC in pool lighting is based on a comprehensive risk assessment that takes into account the potential hazards associated with electrical faults in wet environments, the potential for corrosion and degradation of electrical components, and the need to provide a reliable and low-impedance path for fault current to ensure the proper operation of overcurrent protection devices. The #8 American wire gauge EGC requirement is not simply an arbitrary rule, but rather a carefully considered safety measure designed to protect individuals from electrical shock hazards in and around swimming pools. The function of a ground fault circuit interrupter, or GFCI, is also important to consider. Firstly, detection of ground faults. A GFCI is designed to detect ground faults, which occur when current leaks from a circuit to ground. Secondly, tripping mechanism. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of electricity. Thirdly, sensitivity. GFCIs are very sensitive and can detect even small amounts of current leakage, typically in the range of 4 to 6 milliamps. Fourthly, protection against electric shock. GFCIs provide protection against electric shock by quickly de-energizing the circuit when a ground fault is detected. Fifthly, code requirements. The National Electrical Code requires the use of GFCIs in many areas, including bathrooms, kitchens, and outdoor locations. Sixthly, types of GFCIs. There are several types of GFCIs, including receptacle-type GFCIs, circuit breaker-type GFCIs, and portable GFCIs. Seventhly, testing GFCIs. GFCIs should be tested regularly to ensure they are functioning properly. Eighthly, limitations of GFCIs. GFCIs do not protect against overloads or short circuits, and they do not protect against shock if a person comes into contact with both conductors of a circuit at the same time. Ninthly, importance of proper wiring. GFCIs rely on proper wiring to function correctly, and they should be installed by a qualified electrician. Tenthly, GFCI versus standard circuit breaker. A GFCI is different from a standard circuit breaker, which is designed to protect against overloads and short circuits, but not ground faults. The combination of a GFCI and a properly sized EGC, such as the #8 American wire gauge EGC in pool lighting, provides a comprehensive safety system that protects against both ground faults and overcurrent conditions. It is important to note that the #8 American wire gauge EGC requirement is not intended to replace the GFCI protection, but rather to supplement it and provide an additional layer of safety. The GFCI will detect small ground faults and trip the circuit, while the #8 American wire gauge EGC will provide a low impedance path for larger fault currents, ensuring that the circuit breaker trips quickly in the event of a more significant fault. This combination of GFCI protection and a properly sized EGC provides the best possible protection against electrical shock hazards in and around swimming pools. Now let's consider the installation practices for the #8 American wire gauge EGC in pool lighting systems. Firstly, proper termination. The #8 American wire gauge EGC must be properly terminated at both the forming shell of the pool light and the junction box or transformer enclosure. Secondly, corrosion-resistant connectors. Use corrosion-resistant connectors that are specifically designed for use with copper conductors in wet environments. Thirdly, continuous run. The #8 American wire gauge EGC should be run continuously from the forming shell to the junction box or transformer enclosure without any splices or breaks. Fourthly, secure attachment. Ensure that the #8 American wire gauge EGC is securely attached to the forming shell and the junction box or transformer enclosure using appropriate hardware. Fifthly, protection from damage. Protect the #8 American wire gauge EGC from physical damage during installation and backfilling. Sixthly, proper grounding of junction box. Ensure that the junction box or transformer enclosure is properly grounded to the main electrical panel. Seventhly, compliance with NEC. All installation practices must comply with the National Electrical Code and any local electrical codes. Eighthly, use of approved materials. Use only approved materials and equipment that are listed for use in pool lighting systems. Ninthly, inspection. Have the installation inspected by a qualified electrical inspector to ensure compliance with all applicable codes and standards. Tenthly, documentation. Keep accurate records of the installation, including the size and type of EGC used, the location of the junction box or transformer enclosure, and the results of any inspections. In addition to these installation practices, it is also important to perform regular maintenance on the pool lighting system to ensure that all components are in good working order and that there are no signs of corrosion or damage. This maintenance should include periodic inspection of the EGC connections, testing of the GFCI protection, and replacement of any damaged or corroded components. By following these installation practices and performing regular maintenance, you can ensure that the pool lighting system is safe and reliable and that it provides years of trouble-free service. The potential consequences of not installing the #8 American wire gauge EGC as required by the National Electrical Code can be severe. Firstly, increased risk of electric shock. The absence of the #8 American wire gauge EGC increases the risk of electric shock to individuals in the pool or around the pool area. Secondly, failure of overcurrent protection. The overcurrent protection device may not trip in the event of a ground fault, leading to a prolonged fault condition and increased risk of electric shock. Thirdly, energized metal parts. Metal parts of the pool light fixture could become energized, creating a dangerous situation for anyone who comes into contact with them. Fourthly, violation of electrical codes. Failure to install the #8 American wire gauge EGC is a violation of the National Electrical Code and local electrical codes, which could result in fines or other penalties. Fifthly, liability. The homeowner or contractor could be held liable for any injuries or damages that result from the failure to install the #8 American wire gauge EGC. Sixthly, reduced property value. The absence of a properly installed grounding system could reduce the value of the property. Seventhly, difficulty selling the property. It may be difficult to sell the property if the electrical system is not in compliance with the National Electrical Code. Eighthly, insurance issues. The homeowner's insurance policy may not cover damages or injuries that result from a non-compliant electrical system. Ninthly, safety hazards for first responders. The presence of a non-compliant electrical system could pose a safety hazard for first responders in the event of an emergency. Tenthly, potential for serious injury or death. In the worst-case scenario, the failure to install the #8 American wire gauge EGC could result in serious injury or death due to electric shock. For example, without the proper grounding, stray voltage could energize the water imperceptible but posing a silent threat to anyone entering the pool. Therefore, it is essential to prioritize safety and ensure that the #8 American wire gauge EGC is installed correctly in all pool lighting systems in accordance with the National Electrical Code and local electrical codes. It is not worth taking the risk of potential injury or death to save a few dollars on the cost of materials or labor. The safety of individuals and the integrity of the electrical system should always be the top priority.